Hi guys, today we're going to be looking at LSTMs, bidirectional LSTMs, and RNNs. So, let's state a problem for this presentation. Someone was talking to me yesterday. We were on opposite sides of the street. I had my headphones in and I couldn't hear him. He was yelling, waving his arms, trying to get my attention. I finally took my headphones off and I realized he was yelling at me. He said, "Watch out for the," and then a bus hit him and he was turned into atoms in front of me. He was vaporized. I really want to know what the last word was that this guy was going to say. Watch out for the what? The car, the sky, the birds? How can I know? Here's how I can know. We can use an LSTM and an RNN to recognize his speech and make a real-time prediction based on the context surrounding the sentence and based on where I was. But hold on, an LSTM RNN, what does LSTM even mean? To know what an LSTM is, we need to know what an RNN is. An RNN is a recurring or a recurrent neural network. This is a neural network that takes an input, produces an output, and then uses that output in the next iteration in the input to learn from previous outputs. An RNN remembers every bit of info you give it, and each node in an RNN, so the input, the process, and the output, is a memory cell. In simple terms, an RNN is an artificial network that can self-learn from previous inaccuracies and backpropagate towards the correct prediction. Now that we know what an RNN is, let's take a look at an LSTM. So, long short-term memory is a system that helps an RNN to categorize data into what to forget and what to remember long-term, and what to remember short-term. They help combat the vanishing gradients and the long-term dependency issue in RNNs because they allow the RNN to remember more data and more useful data. They also forget data that we don't need. In simple terms, an LSTM ignores useless data or information provided by the RNN. Since it only has access to past context, it is useful for real-time predictions. What I mean by this is it only has access to stuff that is happening before what we want to predict. So in a sentence like, watch out for the car, it only has access to watch out for the. And it uses that to make its predictions. This is how an LSTM works. It has a cell with 3 gates in it. The first gate is the forget gate. This tells the RNN what to forget and what's contextually relevant or what to remember. It has an input gate, which tells the RNN what new information should be added into the LSTM cell. The cell, by the way, goes into the processing section of the RNN. We'll get into that later. And then the final gate of the cell is the output. This is what should be output in this instance, like what data should be used. Here's how it all works together. Say we start with the sentence, "I need to blank on a diet." We feed this in the input, it processes, and then it outputs something that's not completely right. It then takes this output, feeds it back into the process over here in the state. The state determines what's relevant and what's not. It works through it again, and then we get the answer. I need to go on a diet. This is the most likely prediction. We can determine if this is correct or not. I say that's correct. In the case of an LSTM working with an RNN to predict longer sequences, we can feed it 3/4 of Lord of the Rings into the input. It processes through it. The LSTM knows which parts of the script to remember and which to forget. The output happens, and then it feeds it back into the processing step with the rest of the script, more relevant data, and eventually it might produce something close to the last quarter of the script of the Lord of the Rings. An important note to make, an LSTM is not an RNN. The RNN is the system itself. The LSTM is a subsystem that helps the RNN perform its function. Some advantages of using an LSTM is it helps remember long sequences of information, and it can remember more data for longer. It also avoids the vanishing gradient, so it prevents gradients from becoming too small by using the forget gate. This helps the RNN just generate better data. Some disadvantages is it's computationally complex to run one of these. Training is a lot slower and requires a lot of resources, and there's a lot of hyperparameters that need to be tuned. This is very difficult and time consuming. We also get something called a bidirectional LSTM. A bidirectional LSTM is like Marty McFly from Back to the Future in that it can go forward and backwards. So it's the same as an LSTM, except it has two processes, one processing backwards and one forwards. So in an example named Apple announced a new iPhone, if we have it analyze the word Apple, it can predict that the word Apple is a brand or a proper noun instead of a fruit by looking at the upcoming context, future context, the word announced. The word announced and iPhone tells us that Apple is the company. If we were working with a regular LSTM, we would only have the word Apple and nothing that is to come. Some common use cases for LSTMs are text generation, like a large language model, maybe not entirely what ChatGPT is, but some of it. Bidirectional LSTMs can be used in named entity recognition, like recognizing proper nouns like names and companies. And all of these together can be used in speech recognition and synthesis, like text-to-speech on a Twitch streamer's channel, because LSTMs can predict more than just text. They can predict sounds or videos or images, you name it. Now, let's take what we've learned so far and try to solve our problem from earlier. The man yells, "Watch out for the," then he gets hit by a bus. So we take this sentence and we input it into our LSTM RNN. It processes and it adds the context that we are on a street. We need to be watching out for something, so this is dangerous. And then it outputs a guess. Run this through a couple more 100 times, and eventually we arrive at the most likely prediction: watch out for the bus. "Watch out for the bus," said the man being hit by the bus. This is actually what he was about to say. So in conclusion, LSTMs go hand in hand with RNNs. They increase the memory, they increase contextual processing, they help forget unimportant details, but they are computationally heavy, and bidirectionals can predict text and recognize names. So why an LSTM in this specific use case? Well, here we wanted to know the last word that this man would have said. Since he's no longer with us, we can only guess or predict what he was going to say, and an LSTM is very good at prediction, so it's just about a no-brainer to use it. Thanks, guys. Do you have any questions? Keep them.